this video, we're going to do an example of Lagrange multipliers that involves two constraint equations. Alright, so we're going to find the extreme values of the function f of x, y, z equals x squared plus y squared plus z squared, subject to the two constraints x minus y equals 1 and y squared minus z squared equals 1. So when we do this with two constraint equations versus one, we still do the idea of setting our gradient of f equal to constant multiples of gradients, but in this case we've got two functions that we will have to worry about gradients for, right? We have to worry about the gradient for the function x minus y and the one for y squared minus z squared. So in particular, we're going to worry about our gradient of f being a linear combination, a lambda and a mu, times each of the gradients for the two constraints. So partial with respect to x for the f is 2x. For the first one, the partial is a 1. The second one, the partial is a 0. So we just get lambda times 1 for that first equation. For the second one, the partial with respect to y is 2y. In the other two, we get negative 1 for the first constraint and 2y for the second. So that's why we get negative lambda, because it's a constant times the first one, plus some other constant, a mu, say, times the other one. So we get negative lambda plus mu times 2y. Likewise, the last one, we get 2z equals mu times negative 2z, because that's coming out of the second constraint. We now have 5 variables, so we better have 5 equations. We get the other 2 equations by using the constraints. All right, so let's go through and see what could possibly happen. If lambda is equal to 0, that tells us x has to be 0. If x is 0, y is negative 1. And if y is negative 1, then z has to be 0. So that gives us 1 point to consider, the 0, negative 1, 0. If mu is equal to 0, that tells us z has to be 0. If z is 0, y could be negative 1, which we've already considered. And if y is negative 1, then x is 0 again. We already considered that one. Otherwise, y could be positive 1, which gives us that x is equal to 2. Because from this, if z is 0, y could be plus or minus 1. But if y is negative 1, we've already considered that point. The other one is putting in 1 in here. We got x is equal to 2. So far we have 2 points to consider. All right, well, if mu is not equal to 0, well, if z were equal to 0, we'd have the exact same argument we had in this part. So we're going to assume that z is not equal to 0. Well, then mu has to be negative 1. If mu is negative 1, that gives us negative lambda and then minus 2y, which means we'll get lambda has to equal negative 4y. And if we put that into the first equation, we'll get x is equal to negative 2y. All right, so going through all of that, we're going to substitute this into the first constraint. We'll get negative 2y minus y is equal to 1, which is going to tell us that y is negative a third. But if we put negative a third in for y squared, we will move that over to the other side. We'll get 8/9, but we're saying the negative of z squared equals 8/9, or z squared equals negative 8/9, and that's impossible. So, in particular, if mu is not equal to 0 and z is not equal to 0, then we don't get any other points. So the only two we have are the original two that we considered. The maximum value of this is when we plug in 2, 1, 0, and we get 5. The minimum value is when we put in 0, negative 1, 0. That should say 0, negative 1, 0 there, and we'll get 1 in that case.